introduction. So thank you again for coming. Today we're very happy to have David Layden present here in person. So the title of the talk is Wavefunction Flows, Efficient Quantum Simulation of Continuous Flow Models. And David is a staff research scientist at IBM Research in Cambridge, and he completed his PhD in quantum science and engineering at MIT in 2020. His research is at the intersection of generative AI and quantum computing, and aims to develop connections between quantum physics and dynamical techniques in AI, like diffusion models, Markov chain, Monte Carlo, etc., to benefit both fields. And with that, take it away. Thank you.
Thanks, Carlos. So thank you for having me today. And yeah, as you said, this talk will be about some fundamental connections between some areas of generative AI and on one hand, and quantum computing and quantum physics more broadly on the other hand, connections that are important or have important implications for both fields and yet have largely flown under the radar for, I believe, mostly sociological reasons so far. So I'll start just by giving you an overview. So in very broad terms, quantum mechanics is basically just probability theory, but with the 2 norm and complex numbers. I'll get into that in a little bit more detail later. As far as we know, it gives us the fundamental description of nature on very small scales, things going on at the atomic level in chemistry or material science, for instance. Parallel to that, or because of it, there is a large ongoing effort to build quantum computers that are specialized types of computers that can natively implement programmable quantum dynamics. And how this all comes back to ML is that continuous flow models, which is a term that I'll loosely use to mean flow matching rectified flows, probability flow, DE that you would get from a diffusion model and so on. All of these things in some sense are quantum mechanics in disguise. And a consequence of this is that provably they could be efficiently simulated on a future quantum computer, which would give you a completely new and kind of exotic type of access to the distributions that are learned by these existing models. So just pictorially to give you an overview of what I'll be presenting here, what we currently do today with these generative models is we have training data sampled from some data generating distribution. We minimize some training objective that I won't get into. The details don't particularly matter for what comes next. This is all done on a classical computer, which I'll use to mean not a quantum computer. And so ultimately you learn some score function or some velocity field, and then given these things, you can numerically solve a probability flow, ODE, to do inference, and this gives you samples from a learned distribution that hopefully approximates Q data. And then conceivably, you could have some downstream tasks after this, especially for scientific applications where you might care about say, estimating certain quantities with respect to your learned distribution or something like that. And because you're sampling from this learned distribution, you ultimately have kind of stochastic access to Q sub t. Now, what we do is take this red path here, which is to show that your learned model maps in a very natural way to a Schrödinger equation. And moreover, that this Schrödinger equation can provably and efficiently be simulated on a quantum computer. And what this gives you at the end of the day is some quantum state that encodes whatever distribution was learned by your model. And the reason this is interesting is because now for any downstream tasks that you might care to do, you have a very different sort of access to the learned distribution. So my talk today will have 2 parts. Part 1 is just going to be a broad intro to quantum, and part 2 is going to be on the specific mapping that we call wavefunction flows, as opposed to probability flows. And I'm going to spend quite a bit more time on part 1, or go into at least a lot more detail, because I assume this audience is a lot more familiar with generative models than they are with quantum mechanics. So hopefully, this is accessible to everyone, and if it's not, please feel free to interrupt and ask questions. All right, so in very broad strokes, about 100 years ago, physicists gradually and painfully devised what we now call quantum mechanics or quantum physics, which, as far as we know today, still gives the fundamental description of nature on small scales. And so this underlies everything from particle physics to chemistry to material science and so on. Anything that's small or low temperature basically is governed by quantum mechanics. The undesired feature of quantum mechanics is that it turns out to be very hard to simulate. Everything is naturally extremely high dimensional, and beyond certain simple regimes that are easy to approximate, you're often just out of luck and restricted to simulating very small quantum systems. And so 30 to 40 years ago, people turned this idea of the difficulty of simulating quantum mechanics around, and showed that if you could build a computer that was natively quantum mechanical, that this would allow for more powerful computation. And this is really interesting because from the standpoint of theoretical computer science, every sort of computer is basically equivalent in the sense of any one can simulate the other at the cost of some mild overhead. And as far as we know, quantum computers are really the only exception to this. Not that they can do everything, but that, provably you can count the number of steps in an algorithm and show that they can do some things that, as far as we know, can't be done efficiently on a normal computer, on any normal computer. Now, quantum mechanics has this unfortunate reputation for being really counterintuitive, and there's something to that. But if you're well-versed in probability theory, which I assume everyone in this audience is, you basically already know quantum mechanics. You just maybe aren't aware of it yet. The formalism is very similar. So as I said earlier, quantum mechanics is basically probability theory, but with the 2 norm instead of the 1 norm. And what I mean by that is that if let's say you're dealing with some sort of discrete state space in probability theory, you could describe a random variable by its probability mass function, or if you like, you can stack all the possible values of this mass function into some column vector and form a probability mass vector, which will have non-negative elements that sum to 1, meaning it's a unit norm under the 1 norm. Now, the equivalent quantum state for this sort of setting would be instead a complex vector. And I'm going to use this notation down here, this funny bracket around an arbitrary symbol. Here I'm using the letter psi to denote a quantum state. This is just physics notation, but it's just interchangeable with having a bold symbol or an arrow on top or whatever you prefer. And the key thing here is that this quantum state can be has the same dimension as your probability mass vector, but it can have complex elements. Analogously, if you have a continuous state space, you would have a PDF in probability theory, and then in quantum theory, you have a similar function that we call a wave function usually, that is analogous, but it can be complex valued. So again, for probabilities, you have real and specifically non-negative entries, whereas quantum mechanically, they can be complex. And then the key thing is that when you're thinking about probabilities, the elements, say, of this vector here are the probabilities of the outcomes themselves. Or if you're dealing with PDFs, it's the density. Whereas quantum mechanically, you have to take the absolute value squared, and that gives you the probability. So the outcomes are still random, but this is how you read off the probabilities of anything happening. Now, any operation you might do on a random variable can be described as a stochastic operation. This is what maps, a valid distribution into another valid distribution or preserves the 1 norm. For quantum states, the equivalent thing is anything that I can, or almost anything I can do to a quantum system can be described by a unitary matrix. This is what preserves the 2 norm. So yeah, these are very similar formalisms, except that this move to complex numbers and to absolute value squares, giving us the probabilities, changes everything in some sense. And the key difference is a phenomenon that's kind of loosely called quantum interference, which is basically just saying that complex numbers can add in more interesting ways than probabilities can. In particular, because you can have phases that are opposite each other. You can have 2 different elements of some quantum state get kind of mixed together and just cancel each other out in a way that is just impossible in probability theory. So let me give you an example of the difference just to drive this point home, because really everything that's manifestly quantum comes down to this phenomenon of interference. So to start out with a non-quantum example, just a classical stochastic thing, let's say flip a coin with 50% probability. This operation can be described just by a 2 by 2 stochastic matrix. And so let's say the coin starts off in heads, I'll label that as 0, and I'll use the notation in the top right here. I'll just, denote these probability vectors as one hot encodings. So, E0 meaning heads and E1 meaning tails. So I start in heads, I flip it, and by multiplying by the stochastic matrix, I get, a uniform distribution over the two outcomes. Quantum mechanically, there's not a unique quantum version of this, but all the choices basically behave the same way. So I'm going to just make this one kind of arbitrarily. The unitary equivalent of this operation would be described by a matrix that looks like that U here. And so doing the exact same thing, but now just using physics notation, if I start off with this same vector, which I'll write, with this ket 0, which is just the same thing as E0. I apply this matrix U, and I get a quantum state that's in some sense a uniform mixture of 0 and 1 heads and tails. And so far everything's the same. If I just measured my system here, I would just get a uniformly random bit out. Where things get different though is if I flip the coin again. And so at the top classically, each possible outcome just splits again, right? So if I happen to land in heads, then I split again into heads and tails, and likewise for the tails outcome. And so then if I group all this together, of course, I still just have a uniform distribution again. Now, quantum mechanically, I get the same sort of splitting. The 0 state splits into 0 and 1, and likewise for the 1 state. The key thing being that unitarity forces the signs to be different on the 1 branch. And so when I add this all up, what I actually get back is just the 0 state with 100% probability. And so this is just kind of a toy example, but it's to drive home this idea that stochastic operations that we have in probability theory are kind of analogous, but very different from these unitary operations that quantum mechanics allows us. And so specifically the elements of quantum states, like the populature vector, are often called amplitudes, and they can accumulate or they can cancel in kind of complicated ways depending on their phases, which is what we're seeing here with the one path canceling out. So let me illustrate basically the same math just with a thought experiment. So this is a famous thought experiment from the early 90s, where imagine that we have these sticks of dynamite that are extremely sensitive, the fuse that is. So sensitive, in fact, that it doesn't even take a spark to light them, but that even just a single particle of light is enough to set off this fuse. And the catch is that you have some big stockpile of this, except some of the fuses are missing. And so, some of your dynamite is defective, but it's very hard to tell which is working and which is not, because you can't actually look at it, because if it was working, then it would just explode. And so there's this thought experiment that you can do where you send a pulse of light through a prism that splits your pulse into two, one going through the top, one going through the bottom, and then if you send it through another identical prism again, it will just kind of recombine into the top. And so I'll use 0 and 1 to encode just going through the top or the bottom path. And so if we start off with a beam just going through the top here, then we can describe the action of this prism just by the same unitary matrix I had on the last slide. And so we'll end up just with this uniform mixture of top and bottom like we had before. And then, I apply the prism again. It's the same thing we had on the last slide. I just collapse back to the 0 state, meaning I only ever see light coming out of the top. Now, if I think of sticking a piece of dynamite in the bottom path here, if it's a dud, of course, nothing happens. And so it means that 100% of the time, I see light coming out of the top path. But now if we repeat the same experiment, but we think of putting a working piece of dynamite in the bottom path, then I produce the same state. And if it happens, and either it'll blow up or it won't, depending on whether it was passing through the top or the bottom path. And so in particular, with 50% probability, it'll pass through the bottom and it'll just explode. And the rest of the time, I will end up just back in the top. And so applying U again will produce this state 0 plus 1. And so this is just, again, an illustration of what I had on the last slide. But the reason this is kind of funny is that it means that in this second scenario, if the dynamite didn't explode, with 25% probability, I get light coming out of the top and then 25% light coming out of the bottom. And in particular, that means that if I do this I stick my piece of dynamite in, it doesn't explode, and I see light coming out of the bottom. I've now certified that the dynamite is good, because that's the only way that outcome could happen. And yet I've somehow done that without ever interacting with it, right? No particle of light ever touched the dynamite. And so this is really a nonsensical thing from the perspective of probability theory. It's just kind of showing that this small tweak of moving to complex numbers and the absolute value squared, while mathematically simple, really just changes everything. And you can spend a long time kind of pondering, what happens if you make tweaks to probability theory like this. So in nature, states of quantum systems like electrons and some material are not static things. They evolve in time. And in particular, they evolve according to this first order differential equation called the Schrödinger equation, which is the fundamental equation of quantum physics. And so there's two flavors of this. There's a discrete and the continuous one, just like you would have in probability theory, of Markov chains versus stochastic differential equations, let's say. And so the discrete version of this, in the discrete version, this H term here is just a matrix, a finite dimensional square matrix that's Hermitian. And you can think of it as being analogous to a rate matrix in a continuous time Markov chain. And in particular, if it doesn't depend on time, then the solution can always just be written as the exponential of this matrix applied to my initial state, where this matrix exponential is guaranteed to be unitary because we're demanding that this matrix here be Hermitian. And so this H is called the Hamiltonian, and it kind of describes, so it fully describes the dynamics of your quantum system. And if you're in continuous space, then in principle, things are still the same in some abstract mathematical sense, where now your state is a vector in some L2 function space and so on. But in practice, it's more useful to instead just represent your quantum state by a wave function, which again is analogous just to PDF, but complex valued. And the canonical, and your Hamiltonian now is not just a matrix, but it's some linear operator that acts on functions. And the canonical one that arises everywhere in physics and chemistry and material science and so on just has this form here of a term that looks like a Laplacian plus just a scalar valued function v of x. And for reasons I won't get into here, but if there's any physicists in the audience, you'll recognize these two terms as representing kinetic energy for the first term and potential energy for the second term. And then, more generally in principle, I guess your Hamiltonian doesn't have to have this form. It has to be some Hermitian operator under this, abstract inner product. So that was all quantum physics. Now, IBM and Microsoft and several other companies are racing to build working quantum computers and have been for several years now. And so quantum computers are computers that natively use the sorts of, natively are able to exploit and manipulate the sorts of effects that I've been talking about on the last few slides. And in particular, they're just highly controllable quantum systems on which you can natively implement a large, in a sense, universal set of unitary operations. And crucially, you can do this without having to compute or explicitly multiply these matrices, which in practice will end up being enormous. And so this is sort of analogous to the way in which if you think of this random, say an MCMC algorithm, like a Gibbs sampler, you can make these random moves very efficiently on your computer. And in some sense, what you're doing is applying some very large stochastic matrix to some very large, high dimensional probability distribution. That's how you would analyze the algorithm. But to actually do it, you of course don't have to form these enormous objects. That's just kind of a description of what's going on, but you just do simple operations. And so a quantum computer does basically the same thing, but for this L2 norm version of it. And so in some sense, the difficulty of simulating quantum mechanics would be like the difficulty of analyzing a Markov chain if we didn't have random number generators, like if that was hard for some reason, and you just couldn't do Monte Carlo, you just had to explicitly, calculate your entire probability distribution and then integrate over that. That's basically what we face now for simulating quantum physics, and then building a quantum computer in some sense lets us just do what we do with our normal computers, where you can say integrate a stochastic differential equation instead of having to just solve the Fokker-Planck equation numerically. And then, that's why diffusion models are possible, for instance. And specifically, the way people intend to do this is to use a calibrated set of discrete operations that we call logic gates that are analogous to what goes on just in normal computers that can be combined sequentially to form basically arbitrary unitary operations. And the main challenge to doing this is noise. All of these things are any physical realization of a device like this would be inherently noisy in a way that is kind of difficult to circumvent. And it remains difficult, but the progress in the last 10 years or so has been remarkable, and it shows no sign of slowing. So we're not there yet, but it is definitely something to be taken seriously. Now, what this would give you is a fundamentally different type of computer that exploits quantum interference, the same effect that caused this funny thing with the dynamite a couple slides ago. And this lets you do a completely different type of algorithm that explicitly exploits these phenomena. And we know of such quantum algorithms that are very efficient for certain problems, but the exact boundaries of what quantum computers would be good at are not completely understood. And so formally, we know that quantum computers can solve certain NP intermediate problems efficiently. So the most famous version of this is that factoring on a quantum computer could be done efficiently. And as far as we know, it can't be done efficiently on a normal computer, and hence a lot of cryptography, basically. But contrary to what you might read in the popular news, quantum computers are not panaceas. We don't expect them to give enormous speedups for arbitrary problems. We have to be more targeted than that. And so in particular, a useful or an interesting question to ask is, will these devices be useful at all for machine learning? And this is a tricky question to answer because a lot of the primitives that you would be used to in ML are not particularly well suited for quantum computers. So in particular, we know that quantum computers are not good at finding ground states or even low temperature thermal states of energy functions or analogous quantum things. They're also not even particularly good at finding local minima in some sense, in like the sense of training a neural network. The reason for this is that it's hard to define an analog of backprop that's quantum mechanical, and so it's kind of fundamentally hard to get gradients from some sort of parametrized quantum operation. Moreover, they're not particularly good at problems that involve loading or reading out a lot of data. And a famous example of this is that there's a beautiful quantum algorithm that lets you solve linear systems, so basically inverted matrix, exponentially faster than you could on a normal computer. And so, if you have an n by n matrix, this goes roughly like log n instead of roughly n cubed, which is what you would expect. And this is fantastic, except that then you think of, well, I'm going to have to specify some input vector if I want to solve ax equals b, let's say. And if that has dimension n, then just inputting that thing takes time n. And so who cares if I'm exponentially faster on the rest of it? That's not the bottleneck. And so this is kind of a recurring issue with quantum computers, that they're extremely good at some things, and yet they get bottlenecked really easily by large data or messy situations and so on. And so to not sound too pessimistic, now let me give you the canonical answer to what are quantum computers known to be good at. And they're known to be efficient for simulating the Schrödinger equation, namely for simulating the dynamics of quantum systems. And I would argue that this is the most important differential equation in the world. And indeed, this is where the idea originally came from Richard Feynman and co. in the 80s. And this in itself is very important for science. Simulating quantum physics is hugely important in chemistry and materials physics, and in some sense it provides you a sort of computational microscope and lets you get a handle on things going on at these small scales in a way that we just fundamentally cannot have otherwise. But then a natural question to ask, or a way to approach this, is what non-quantum problems can be mapped to simulating quantum dynamics. And so it turns out that the factoring problem in some sense actually can be understood in this way, and likewise with search. And now what we show in this work is that flow-based generative models, meaning diffusion models, flow matching and so on, also kind of map very naturally to quantum dynamics, which is what quantum computers are particularly well suited for. And just to give you a flavor for how people intend to simulate quantum dynamics on a quantum computer, even though I was saying earlier that quantum computers are meant to be digital, so they have these discrete operations that they do. What you can effectively do is something just like Euler's method. So just the simplest version of this would be if I have some quantum system, of interacting electrons, let's say that I want to simulate, and it's Hamiltonian H, which describes the dynamics, can be written just as a sum of two terms, A plus B, let's say, each of which is simple. And in particular, where I know how to implement just the exponential of A by some desired rotation angle and the exponential of B separately, then this doesn't quite get me all the way there because we're dealing with matrices here, and so just unlike real numbers, because A and B generally won't commute, the exponential of A times the exponential of B is not the same thing as the exponential of their sum. However, if I take really small time steps, this is approximately true. And so in particular, if I kind of toggle back and forth between taking a little step by A and a little step by B, and I repeat this many times, what I get overall is the desired evolution plus some remainder term that I can make arbitrarily small just by taking my time steps to be small. And so, if the Schrödinger equation of my real system in nature follows the purple curve, then in effect, I can sort of take little time steps in blue and kind of kick the state of the quantum computer back and forth in such a way that it provably stays close to the true answer. And so, you can do this more formally, but roughly speaking, to keep the discretization, if I'm not going to produce the exact desired state, I'm going to be epsilon away. And so if I want to keep, if I have some target error tolerance epsilon, then I just need some number of time steps r that scales like the time squared over my error tolerance. And this is basically exactly Euler's method or tau leaping from discrete diffusion models, except that everything is unitary here instead of stochastic. And there are lots of more sophisticated variants too. Let me just give you another flavor of kind of a similar idea. You can use these same sorts of tools to realize all sorts of interesting dynamics. So if instead my Hamiltonian was some commutator of two matrices A and B instead of a sum of them, I could basically play the same game, but I could use a different sequence of steps. So instead of just going A, B, and so on, I could do A, B, minus A, minus B. And if you expand this out to leading order, you find that that you can basically play a similar game and simulate these dynamics in kind of a tau leaping way. And then just to wrap up this topic, what about continuous things? Lots of things in nature are not discrete. So as I had on an earlier slide, the canonical Hamiltonian that we deal with for continuous systems has this form here, or I'm just writing it in a single spatial dimension. And basically you can do this in the way that you would imagine. You discretize space on some fine grid, and then instead of dealing with a wave function that's like a PDF, I kind of map this to just some finite dimensional vector of wave function at all the points. And then my derivative term gets mapped to some finite difference tensor for some small step size h, and my pointwise multiplication by some potential function v here becomes just applying a diagonal matrix. And there's two things that make this tick. The first of all is that, for reasons I won't get into, we can basically always efficiently implement diagonal unitaries on a quantum computer. So taking a small time step by the v term is going to be easy. And conveniently, this k term is diagonalized by a discrete Fourier transform. And also very conveniently, we can do that efficiently on a quantum computer. This is a unitary operation. And so it means we can basically just use the techniques from the last slide, just replacing the exponential of this k term by its diagonal in a Fourier transform on either side. And so we kind of just go back and forth between like a spatial domain and a frequency domain as we take these little Euler time steps. All right, so that's a whirlwind tour of quantum physics and quantum computing and everything you need to know about that. Before I dive into the second part, are there any questions from the audience? All right. Okay, so one last manifestly quantum thing, I guess, before bringing this back to ML a little bit. So I'd like to talk about a specific type of quantum state that's called the coherent encoding of a distribution, or sometimes called the Q sample for short. So if I have some either probability mass function or PDF Q, then the quantum state that's just the square root of that thing is called the coherent encoding or the Q sample. And so if I have a system in nature or a quantum computer that is in this quantum state, and I just measure it, then I'll get a random sample back, and the probability or the probability density of any particular outcome x is just the absolute value squared of this thing, which is just q of x. So it's just identical to being able to sample from this distribution q, except that having this sort of quantum state is in some sense more powerful than being able to sample from the underlying distribution, because you are allowed to act coherently or apply unitary operations that are allowed by quantum mechanics before doing this final measurement. And so this gives you this kind of bizarre toolkit that we just don't have access to in probability theory. So a canonical example of what does this buy you is if you wanted to do Monte Carlo estimation, say of the mean of some function f with respect to this distribution q. You can do this with quadratically fewer q samples to reach a given target error than it would take samples. And the reason is that the math is basically the same, except that quantum mechanically, everything kind of takes place at the levels of the amplitudes, which are just the elements of your vector. And so when you square things, in some sense, you get an uncertainty that looks like 1 over the number of samples instead of 1 over n squared, which is what you'd be more used to classically. But you can also do kind of a broader range of things that is not particularly well studied. So I was saying earlier that in order to simulate nature, we make heavy use of these discrete Fourier transforms that quantum computers are good at. That means that you can apply a Fourier transform to your probability distribution and sample from that, which is something really just has no classical analog. And so what this would give you is high probability of sampling at frequencies that correspond to, or that show up a lot in the distribution Q. So you could find hidden structure quickly in a very non-local way by doing these sorts of quantum operations before measurement. The flip side is that we're not particularly good at preparing these sorts of quantum states. And I don't just mean in practice, I mean even in theory, besides just very simple ones like square roots or Gaussians or things like that. We have a very limited knowledge of how to prepare these states. Typically, the techniques rely on mixing or on quantum analogs of Markov chains that can be slow mixing in general when you're dealing with complicated distributions. And moreover, we believe this to be a hard problem in general in a complexity theoretic sense to prepare these sorts of quantum states. Now I'm going to change gears completely and talk about what this all has to do with generative models. And so in particular now, I'm going to assume a lot of knowledge about this topic from this audience. So consider probability flow ODE, where I have some learned velocity field v of t, and this defines a flow model. And what I'm going to do is numerically solve this with some random initial condition q naught. Then, of course, the marginal density or the law of x of t satisfies the continuity equation as usual. And so to kind of combine these sorts of flow models with quantum mechanics, a reasonable question to ask would be, what is the equation of motion for the Q sample or the coherent encoding of this law of x of t? So in other words, this thing is a wave function. It's just square root of Q of t. How does that evolve in time? And this turns out to be very easy to work out. So you can take the time derivative of this thing. I'm going to put an I out front here because I know the answer already. But this is just a chain rule through the square root. You can then plug in the continuity equation where everything basically looks like we normally have, except we have this kind of dividing factor by psi of t out front because of the chain rule. I can just expand out this product just using normal calculus identities, and then simplify things a little bit. In particular, just divide out this psi of t that's at the bottom here. And what I'm left with is actually a form of the Schrödinger equation. In particular, I can define some linear operator that I'll call the continuity Hamiltonian, because it's in some sense the square root of the continuity equation, that just acts like this here. I'll have more on the next slide, but it acts like a gradient dotted with your velocity field plus the conjugate of that thing. And again, for any physicists in the crowd, this minus I nabla term you might recognize as just the momentum operator from quantum physics, but that's kind of tangential here. The key point being that that it's very simple to show that if some marginal distribution satisfies the continuity equation, then its square root, some quantum state, obeys the Schrödinger equation with a funny Hamiltonian. Right, and so that's what I have written here. And there's an important special case that we'll largely focus on here, which is the case where your learned velocity field is conservative. So where lowercase v of t is just the gradient of some scalar valued v of t that maps vectors to scalars. And so this we can always, as far as I understand, we can always insist on a conservative velocity field if we want. And there is a framework already for that was already known called action matching for learning this explicitly. But of course, it's already kind of implicit if you come at this from the perspective of diffusion models, because the score in principle at least should be a conservative vector field. And so in this special case, the Hamiltonian that you get from the continuity equation simplifies to just a commutator between the first term that looks like a Laplacian and the second term that's just this function v of t that gives you your velocity field. And this is interesting because in quantum physics, these two terms are interpreted as representing kinetic and potential energy respectively. And so what's really interesting about that is that we end up with this Hamiltonian, this continuity Hamiltonian that describes flow models that has the same two components as the one that describes all of nature, basically, as far as we're aware, except they're combined in a slightly different way. And so as far as we know, this continuity Hamiltonian doesn't actually arise in nature. But then to bring this all back to the quantum computing part, one of the big motivations for quantum computers was to be able to simulate physics and Hamiltonians like on the bottom here that arise in nature. But actually, we're pretty flexible about the exact details of it. And so in particular, we can handle the Hamiltonians that arise instead from flow or diffusion models just as easily. And so a large part of our paper on this topic is basically just proving that. Our current quantum computers are too small and too noisy to actually implement this sort of experiment, but we can do the analysis easily enough. And again, even though these Hamiltonians that describe flow models don't arise in nature, they can be handled in more or less the same way using the sorts of ideas that I had in the first half of this talk. And so what you need to do is basically the same sort of analysis that you would do if you wanted to bound the error of a particular algorithm for solving stochastic differential equations using finite time steps. So you have to, account for the fact that you're discretizing space, and that takes a lot of work. You have to deal with the fact that you have explicit time dependence in these things, and then also make sure that all the operations that you actually end up with are friendly for quantum computers in the sense that we actually know how to implement them in terms of our discrete operations that we've tuned up. And so in some sense, it's like analyzing Euler's method or some Runge-Kutta solver in the age of vacuum tubes, like where you can't actually do it yet. And so what you have to do is prove how everything will scale with all your parameters. And I won't get into the details here, but the gist of the story is everything is efficient as we expect it to be, even though this particular sort of thing has not been studied before, as far as we're aware. And so just to illustrate how this all comes together now. So in generative ML, you have this probability flow ODE that you solve numerically from some random initial condition that's in the simplest case, say just a standard normal distribution. And so then the marginal density of your state evolves according to the continuity equation. Or equivalently, you could say that solving the probability flow ODE with a random initial condition is a Monte Carlo simulation of the continuity equation. And so then the way we do generative modeling of this type is we have various methods for learning good velocity fields here. And so having learned a velocity field, we solve this ODE, and out of this we get a sample from some distribution that should resemble our data generating distribution. And so what we show is that this continuity equation maps to a funny version of the Schrödinger equation that crucially involves just the exact same velocity field you've already learned that can just as easily be run in principle on a quantum computer than on a classical computer. And so as quantum computers become more and more mature with the intention of simulating nature, as an interesting byproduct, we also get the ability to probe or to access our current flow or diffusion models in a very different way. Namely, by just simulating the dynamics of this Hamiltonian here, you would produce the quantum state square root of Q1, where Q1 is just the distribution that you learned in your flow model. And then if you just measured the quantum state there, you would just get a sample from Q1, just as you would from the way we do things now. The reason this is particularly compelling is if you're doing, say, AI for science type things, and you care about, this sampling is not the final step, then having this sort of quantum access to your distribution opens up a whole new range of operations that we just don't have access to today. So I like to think of this as inference through interference. And to summarize things, what this all shows is that flow models are an unusual type of quantum dynamics in disguise. And what that means is that as quantum computers mature, they will provably give us a fundamentally different and potentially more powerful type of access to the learned distribution of these models. And so one way that I like to contextualize this result or this line of work is in the context of this nice paper from the Meta people, and some of whom are at MIT, where they have this table that's kind of a taxonomy of different types of Markov processes that can be used, that are used for generative modeling. And we can now firmly say that quantum dynamics is a column in this table. The way that we've done it is certainly not the unique way to approach it, but because we kind of piggyback off of the existing formalism, there's no need to learn anything new or anything like that. We can just kind of take your current velocity field and just provably run it on a quantum computer, and you get a different column of that table, and what else lies in this space remains to be seen. And so in particular, a natural question is, what exactly would you want to do, or could you do that's interesting with this sort of quantum access to your learned distribution? So as I said, the canonical example is that you can do Monte Carlo or like mean estimation with quadratically fewer samples, if that's something that you care about. But I also hinted that you can also do all sorts of interesting non-local things, like having to do with Fourier transforms of your learned distribution. And here there's a funny cultural barrier because the quantum physicists that know these sorts of things typically are not all that well versed in the ML models, and so have no idea what would be interesting there. And then likewise, for the ML people, there has been no reason so far to think about these sorts of tools because you don't have, you have no way to access them. And so here we're kind of faced with this interesting situation where we can't do all these things yet, but we will eventually. And so it's interesting to think in the meantime of what would that buy you. Another related question is, can you get a speed up just for sampling with these sorts of methods? So what I presented now, we can kind of keep track of the number of steps that are required on a quantum computer, and the scaling is comparable to just simulating an ODE classically. But you don't, if you just measured your quantum state to just get a sample, it's not particularly faster than just the way we normally do inference. However, there's a whole slew of techniques for simulating the Schrödinger equation on quantum computers that are significantly more efficient than the ones that I showed earlier. And so it's interesting to think about whether, even if you just care about sampling, whether in the long run you would eventually actually just want to do it on a quantum computer and just do the measurement that way. Similarly, a lot of the math here works in particular for the continuity equation, but less well for the Fokker-Planck equation. And it's kind of interesting to think about what goes wrong, or if there's anything to be done in that space to pull on the thread a little bit, and likewise what can be done in the landscape of discrete diffusion. And this is particularly interesting because actually the discrete setting is quite a bit more natural for quantum computers, and so that's kind of a pressing thing to work on. And then in the same spirit of, what could you do with this new type of quantum access? It gives you an interesting different set of controls, a different set of knobs to turn than you currently have now. And so it's interesting to think of this as if this could be useful, say, for tilting a learned distribution. This is just speculative, but what happens if you add some extra perturbing term to the Schrödinger equation? How does that affect the samples? We have no idea, but it's also something that is just completely outside the scope of this normal analysis. And so it's interesting to think about if that gets you anything new. And then finally, just to wrap up, from the more fundamental or theory side of this, an interesting element of this result is that it gives you a sort of Rosetta Stone between these two fields that on the surface have nothing to do with each other: quantum physics or quantum computing on one hand and generative modeling on the other. And what I mean by that is that it lets you now cast questions from one field as being questions from another field. So if you're a quantum computing person and you want to know, is it possible to prepare this coherent encoding, this Q sample? Well, now that's equivalent to just saying, can a flow model learn the following distribution? Or to go the other direction, it's believed on complexity theoretic grounds that there are distributions from which it's easy to sample from and yet hard to prepare Q samples for these quantum states. And so that would seem to imply that no flow model could learn those distributions. Otherwise, you would immediately have a way to prepare the Q samples for them. And so it kind of suggests that even if you don't care about all the future quantum computing stuff, that in the theory of these sorts of generative models, that by taking complexity theoretic statements from quantum computing, that you can just immediately imply new limitations today on flow models. And so on that note, I have to thank my collaborators, mostly colleagues at IBM or former colleagues, and also Kirill Nekludov at Mila, now on leave at Anthropic. And I'll leave you just on this summary slide and thank everyone for their attention.
Thank you. Thanks for the great talk.
Yeah, of course.
So we can open up the floor for questions, maybe.
Yeah.
I have a couple of questions.
Yeah, sure.
So you talked mostly about inference.
Yeah.
So that's assuming that you have PT that's learned and that you just want to do inference, right?
Yeah.
Is there anything new that can be said about training, like does training change, or would that be in principle the same thing?
So for now, it was deliberately the same thing. And the reason for that is that there was a lot of people have tried to construct analogs of neural networks that used quantum operations. And there are a lot of known barriers to training these things. In some sense, the fact that quantum states kind of collapse when you measure them places some hard limits on your ability to do this. And so, yeah, in this work, we kind of deliberately tried to say, what if we leave learning the same? Sure. How can we map that? So potentially in the future, but that's something we were trying to avoid for now.
And the question I had is more about you mentioned this equivalence, like a complexity equivalence between preparing states and or I guess the concept that I'm trying to clarify is what do you mean by preparing a state, and why is this challenging?
Oh yeah, so there's it comes down to the fact that broadly, or like in general, like theoretical CS terms, this task of preparing this sort of quantum state on a quantum computer is a hard one, in the sense that there exist states that we don't expect any quantum computer can efficiently prepare that are of this form. And in particular, I believe what's funny about it is that some of these correspond to distributions that should be easy to sample from. And so there seems to be this kind of, this step is a hard one in general, that there should be distributions that are kind of simple classically, and yet the square root of them is a complicated object. But then the argument was that because we now have a mapping from these flow models to preparing those square root of states, that if you believe on complexity theoretic grounds that there should be no way to prepare that, then that should also imply that there should be no model that can learn the underlying distribution.
I see, because preparing a state basically means that you can start off from a state that you have access to, and then run the Schrödinger equation to get the other one.
Yeah, exactly.
I see.
So there's like a discrete and a continuous time picture, I guess, of this. The continuous time one is what you said of like, could you kind of evolve by the Schrödinger equation, get there? And then there's like the discrete time one, which is more the computational one, which is can you use like some small number of discrete operations on a quantum computer and get epsilon close to that or something?
I see.
Yeah.
And then, so is it the first time that people have used commutators, like Hamiltonians that are expressed as commutators, or like is this completely new, or like have this kind of objects appeared before? Because I guess, yeah, commutators are very common in quantum mechanics. So I was wondering.
Yeah, this particular one, I'm not aware of it coming up before. I can't say that broadly speaking, there haven't been Hamiltonians with commutator terms. The way in which commutators arise, like that with the uncertainty relation in quantum mechanics, you're right, is a very famous thing. As far as I'm aware, them actually arising as the generator of dynamics is much less common. So I don't know that this is the first time, but this particular one, as far as I'm aware, is new.
And in terms of like being able to make sure that everything works out as you mentioned, like what were the steps for that? Did you just have to make sure that what were the steps to making sure that you could compute the exponentials of the terms in the commutator?
Oh yeah, so we used something called pseudospectral Fourier method. I don't know if it's like a thing from numerical analysis. It just happens to be very friendly for quantum computers as well, where the idea is that you can always, if your solution, like if Q of t, let's say your marginal distribution is reasonably well behaved, in principle you can always express it as some infinite Fourier series. And if instead of it being an infinite Fourier series, if it truncated at some finite number, then there would be no discretization to do, because you could kind of just keep track of the Fourier coefficients or equivalently of like in the spatial domain of some representation of that. And so basically, much of the analysis consists of just bounding how much error you would incur by kind of throwing away all those high frequency components. And so you can and because when things are smooth, Fourier series or Fourier coefficients decay fast, you can kind of bound these things nicely. And so what you end up with is kind of a mixture of matrices that are either diagonal or that are Fourier transforms, and that kind of just arises from the formalism, from this like numerical methods formalism. So that was kind of the underlying analysis.
I see. And in terms of experiments, is it possible to run experiments on this, or?
No, so this is like significantly out of reach of current quantum computers. But I will say that one thing that's sort of appealing about this is that because there is kind of this theory bridge between the classical models where maybe you don't necessarily know how close your learned distribution is to your data distribution, but you can formally guarantee that that you'll produce a quantum state that's arbitrarily close to that, the one for your learned distribution. Then in principle, you could imagine doing some sort of just normal ML experiments, and then you can kind of use your analytical results to say, this is what would happen on a quantum computer, provably, because this is what happens classically. Like for instance, there's, we can talk about this more offline. Actually, okay. I don't want to bore everyone with the.
Oh no, that's great. Yeah, I guess. Any more questions from the audience? Let's thank David again for the
thank you very much.
Yeah.